Alright everybody, welcome back for video 2 of section 9.3 of AP Calculus BC, finding arc lengths of curves given by parametric equations. So we're going to do one more example here. Now we're really, on the AP exam, they say, we're responsible for finding the length of smooth curves. Here we're going to look at a curve that is not smooth and kind of show you how to deal with that. And we're going to use some of the symmetry ideas that exist in these parametric curves in order to help us do this. So the first thing I'm going to do is take a look at this curve that we are going to find the arc length of. So let's go ahead and, do I have 0 to 2 pi? Yep, I have 0 to 2 pi. I think my x and y values should work okay. We might need to adjust those though after we've graphed this. So we've got cosine cubed of t and sine cubed of t as our x and y functions. And let's go ahead and, well, we'll make sure that this is on path. And let's take a look at the graph from 0 to 2 pi. Not too bad. We get a decent view of the curve here, but I'm going to even move in on this a little bit more. Go ahead and go from -1 to 1 in both directions. See what this graph looks like. There we go. And to get an even better idea, since I know I'm going to want to use some symmetry to help me find the length of this curve, I'm going to use zoom square, which I think is an underutilized zoom on the calculator. I'm going to use zoom square to take out the stretch distortion that exists in the graph. And now we have a curve that looks like this. Alright, so you see places where there are issues. There are cusp points here, and here, and here, and here. And some of those are going to cause us to have some difficulty and some problems getting around those cusp points. Something else that you should notice, if I trace this, I could just find the length of this curve from time 0 to, it's like time pi over 2, and multiply that by 4 to get the length of the whole curve, since it forms a diamond with those 4 symmetric pieces. But I'm not going to do that. I'm going to get even a little bit more kind of tricky here with using symmetry. I'm going to go ahead and, oops, scrolling the wrong way. Come back down here, right there. Pi over 4. If you look at pi over 4, this curve is split into 2 perfectly symmetric pieces, from 0 to pi over 4, from pi over 4 to 2, or pi over 2, pardon me. So I could take the length from 0 to pi over 4 and multiply it by 8 and get the length of this whole curve. Alright, so I've got a bunch of options that I could try. Let's go ahead and we'll see how some of these work. I'm going to start by using the one where I'm going to just take 8. So we're going to multiply by 8. We're going to take the length of this curve from 0 to pi over 4 of the, I need dx dt and dy dt. Dx dt here is going to be equal to, let's see, don't forget, cosine cubed of t is cosine of t, the quantity cubed, so we want to make sure we use the chain rule. It's going to be derivative of the outside, leaving the inside the same, times the derivative of the inside. So dx dt is -3 cosine squared of t sine of t. And dy dt is going to be 3 sine squared of t times the derivative of sine of t. So it's going to be that. And this should give us the length of this curve. And I'm going to go ahead and use my calculator to calculate this. So we're going to take 8 times the integral of the square root of the quantity -3 quantity cosine of t quantity squared times sine of t, that whole quantity squared, plus quantity 3 quantity sine of t quantity squared times cosine of t, that whole quantity squared, close the square root, from t, with respect to t, from 0 to pi over 4. And we get 6 for our arc length here, 6. Now again, I could have probably done this by hand. In fact, I'm going to do it by hand in the end here. But this is going to be equal to 6. So we know our target here, our target answer is 6. I'm going to go through the process of doing this by hand then also. We could also have tried to find this as 4 times the length of each of the pieces, which would have made this 4 times the integral from 0 to pi over 2. Let's see if my calculator will do this one. Also gets 6, so that worked out. I could have tried to take the integral of the whole curve. Let's see if that works out. Take those multipliers out and just take the integral from 0 to 2 pi and see if that works. Maybe my calculator is powerful enough that I can handle all of this stuff without any difficulties. I'm waiting for you, calculator. Looks like my calculator's struggling. It's probably struggling getting over, it worked pretty quickly, pretty easily for the 4 times the integral from 0 to pi over 2. It's probably struggling a little bit at pi over 2 where that cusp point is, which is why it can be important for us to split these up into intervals where the curve is smooth. It doesn't cause as much of a problem for us. Well, that's busy. We'll see if my calculator can churn that out. But while we're waiting for that, I'm going to go ahead and do this one by hand. So what I'm going to do here, I've got 8 times the integral from 0 to pi over 4. I'm going to simplify what's inside the radical here. It's going to be 9 cosine to the 4th of t sine squared of t plus 9 sine to the 4th of t cosine squared of t dt, which is going to be equal to, and inside my radical here I can factor out a 9 cosine squared of t sine squared of t, and what's left behind is cosine squared of t plus sine squared of t. Now, of course, we know that this particular piece right here is 1, and so we've turned this 2-term expression under the radical into a single-term expression. Not only that, we've turned it into a single-term expression that we can easily take the square root of. The square root of 9 cosine squared of t sine squared of t is equal to 3 cosine of t sine of t dt. So I can bring the 3 out in front here. And now this I can go ahead and just integrate using substitution. If u is equal to sine of t, du is equal to cosine of t dt. And so this turns into 24 integral of u du. I'm going to change my limits of integration based off of my substitution. Sine of 0 is 0, so that's going to stay as is. Sine of pi over 4 is root 2 over 2. And now integrating, this becomes 24 times u squared over 2 evaluated from 0 to root 2 over 2. So that's going to be equal to 12 times root of 2 over 2 quantity squared minus 12 times 0 squared. And that becomes 12 times 2 over 4, 12 times 1/2. And so the length of that curve is 6. Oh, my calculator finally broke down. It could not find, if you see my output here, it could not find the length of the curve when I tried to do it as the whole curve, which again illustrates the importance of, when we have symmetries, using them to break down curves that are not smooth. All right, interesting example. That brings us to the end of this section, and come on back and join us next time for section 9.4, where we are going to start defining and differentiating vector-valued functions. All right, see you next time. Have a great rest of your day. Bye-bye now.